So under this, we will be having, that is, 2 NOR gates and 2 AND gates in order to represent the logic diagram. We can see here it is a single input flip-flop developed by JK flip-flop by connecting J and K together as T. The output is dependent on input, but how is it? That is by using 2 power n. Here it is completely opposite. We'll be having 8 input bits and only 3 output bits. Hello everyone, I welcome you all to the second session of Unit 4, that's under Digital Computer Organization, and the 4th unit is all about combinational and sequential logic circuits. We have one more video before this, so if you want to learn more regarding your basic things, then you have to go back and check with the first session. Over here, my name is Deepa Kutnikar. I am working as an assistant professor at the Department of Computer Science, Vidhyaashram, Temple of Excellence, MYSURU. So let's go forward and let's see what's the recap of our previous session. In our previous session, we have discussed a difference between combinational as well as sequential logic circuits. Then we also did discuss what is a adder. Then under adder, we have different types like a half adder, full adder. Under these adders, we did discuss the basic block diagram, circuit diagram, or we can call it as a logic diagram of the adders, and then the number of inputs, the number of outputs, what is the expression for the outputs. With respect to subtractors, also we did study what is a half subtractor, full subtractor, expressions of the output for half as well as the full subtractors, and we also did learned the truth tables regarding these things. So if you want to learn more regarding these things, you have to go back and check the first session. Alright, let's move forward and see the agenda of today's session. Yes, in today's session, we will be learning about flip-flops, like what is a flip-flop and what are the different types of flip-flops. Then followed by, we will be learning what are decoders. So under decoder, we'll be having 3 to 8 lines decoder, then followed by a encoder. We are specifically learning what is a octal to binary conversion. So these are the things what we discuss in our today's session. So let's get started with our basic flip-flop. That's none other than a simple SR flip-flop. So before heading up with the SR flip-flop, let's understand few basic regarding flip-flop. Flip-flop is a type of sequential logic circuit where it is being used in order to store the outcomes, or we can say store the number of bits. It is a basic building block of any digital circuits. So this is all about a flip-flop, and heading forward, let's understand the types, and under that the first basic type is SR flip-flop. SR, S in the sense set and R in the sense reset. So altogether we can call it as a set reset flip-flop. So under this, we will be having, that is, 2 NOR gates and 2 AND gates in order to represent the logic diagram of this SR flip-flop. Yes, let's see a simple block diagram of SR flip-flop. So here we can observe the flip-flop is correlated with the clock. Only when you get a clock pulse, only at that time our flip-flop starts working. Clear? So yes, these are the 2 inputs, that is S as well as R. Up next, what is the output? The 2 outputs are none other than our Q as well as Q dash. So yes, Q is a current output and Q dash is a complemented form of our current output. Alright, let's get back here and let's see the truth table of this SR flip-flop. We are dealing with 2 of the inputs. So our combinations will be 4, that is 0, 0, followed by 1, 1, then 0, 1 and 0, 1. Now, with respect to this context only, let's see what is the output. So if we have, that is, both the inputs as 0, then the output will be the previous state. Then if my input is 0 and the output is 1, then at that kind, we get output 1. So that condition is called as reset. Okay, then followed by, if one of my input is 1 and R is 0, at that time also I'll be getting a output 1. So that condition is called as a set condition. Clear? Then followed by, if both of my inputs are high, at that time the output is intermediate form, or we can say has a invalid form. So this is a simple truth table and the description of the outputs. Let's move forward and see the basic logic diagram of a SR flip-flop. Yes, as I told, here we will be using two NOR gates and a simple AND gates. This is a logic diagram. Here you can see here the output is considered as one of the input for the second stage, right? So this is how the feedback is made possible. So what is this called as? It is none other than a feedback network. Okay, so here you can see here the output. A part of output of Q bar is considered as the input for the second stage. So yes, this is none other than our feedback networks, and this is a complete logic diagram for a simple set reset flip-flop. Next type of flip-flop is a JK flip-flop. A JK flip-flop is a modified version of the SR flip-flop where the invalid state, that is when both the S and R was 1, at that time our output was invalid, correct? So here, in order to overcome that invalid state, we are heading with the update, and that is none other than a JK flip-flop. Alright, here we have two inputs, that is J and K, which is more similar to our S and R type of flip-flops. Okay, now this is a simple block diagram of JK flip-flop where the most important point to note is a clock. Clock is there. Along with the clock, we will be having two of the inputs, that is J and K. Clear? So this is the input part. And we have two important signals, that is a preset as well as a clear. So this is a preset and this is a clear. Okay, so these two are also a part of symbols, but why it is used? It is used as a control signals. When it is used? Whenever we need the output as 1. Okay, at that time our preset will work. Whenever we want our output as 0, at that time our clear condition or a clear input will work. Okay, so these both are active low, and we can say these both are very important in order to go with a practical JK flip-flop applications. These are the two input signals. Yes, even preset and clear is also considered as input signals itself. Next, the output is none other than our Q and Q bar. Okay, the Q and Q bar are the two outputs. This is all about a simple block diagram of a JK flip-flop. Next, let's head and understand what is a truth table as well as a logic diagram of a JK flip-flop. Starting with a logic diagram, here we can see we are using 4 NAND gates. 1, 2, 3, 4. 4 NAND gates are used, and also we can observe here, even here we are using a feedback circuit. The part of the output is considered given as an input to the second part, correct? So this is called as a feedback network. Okay. So this is a simple feedback, and as we can observe over here, we have two of the inputs, that is J and K, along with our clock, then followed by the two outputs Q and Q dash. Up next, let's see a truth table, that is with respect to J and K. As we know, there are multiple inputs along with J and K. What is it? It is a preset, clear and a clock. So one thing to be noted here is whenever you want your JK flip-flop to work, at that time you want all this supporting inputs to be high. Only then the JK signals will be considered, or the inputs of JK will be considered. Clear? So let's have a look here. As you can observe, we have a preset 0 and a clock 1, followed by a clear 1, and the clock is not defined. Okay, at that time what is the output? It is a set which is ready to take the input. Okay, so up next, if my input is 1 and if my preset is 1, also the clear signal is 0, then our clock J and K are not at all defined. At that time our output will be 0, and that is called as reset. followed by if my preset is 1 and clear is 1, but clock. So you can observe here even the clock, preset and clear play their important roles. So all of this should be high, only then we will be getting a proper output. So now let's see what is the output. So if clock is 0 and J and K are not at all defined, at that time our input will be the same as that of our previous set. Clear? Now let's see here when the preset, clear, clock all are 1. Along with that, we have different combination of J and K, that is both are 0. At that case, so from here we can say the exact J and K starts. Why? Because all the signals are high here. So now the thing, when J and K are 0, then the output will be the initial stage, that is 0. Whenever J is 0, K is 0, then at that conditions our output will be the same as that of our previous state, and Q dash will be a complement of that. That state is called as initial stage. Done. Up next, if we consider 1 and 1 for both the things, that is for J and K, both are high, at that time we will be getting the output as 1, and that output is called as set. Clear? And again, if my J is 0 and K is 1, at that time the output will be 1, and that condition is called as a reset condition. Next, the main condition, whenever all the bits are high, at that case we will be having our J and K on-ing, offing. That is a continuous state where the outputs will be continuously toggling in the sense on off, that is continuous on off. At that time we call that condition as a toggle condition. So this toggle condition is one of a drawback of our J and K flip-flop. Why it is a drawback? Because of continuous on and off, that is under one cycle. Let's consider an example over here. Okay, so now this is a clock. So what do you think, for one clock the J and K will work in this case, correct? It should work with respect to 1 cycles. It is not a point here. So with respect to J and K, what happens is it will be continuously on-ing, inside a single cycle of clock. When this happens, then a lot of memory will be consumed and the circuit will be continuously working, and that state is called as toggle state. And this condition is called as race around condition. What is it called as? This condition is called as race around condition. So this race around condition is a drawback of this J and K flip-flop. Now let's head forward and see which is the next type of flip-flop. So yes, the next type of flip-flop is MSJK. MSJK is none other than master-slave JK flip-flop. Here we introduce a concept of master and a slave in order to overcome one of a drawback of JK flip-flop. That drawback is none other than a race around condition, what we discussed. In order to overcome that race around condition, we will be moving forward with our MSJK flip-flop. Yes, MS in the sense the master, it forms a first stage and the slave forms the second stage. When the first stage works, yes, it works only when the clock signal is 1, and the slave works whenever the clock signal is a 0. So this is a main important point to note, like when the master will work and when the clock will work. Now let's see how is it this master and slave are connected. Yes, it is connected in a serial way. It is connected in series. So by considering this master slave flip-flop and control clock master slave, we can control the toggling condition. So we can say the race around condition of a JK flip-flop will be minimized, or it can be completely nullified by using this MSJK flip-flop. So let's see a basic block diagram. Yes, this is a block diagram. Here, as we can see, the first stage is a master stage and the next stage is a slave stage. But as you know, the clock, whenever the clock is directly 1, only at that time the master will work, and it has to be complemented, correct? So in order to complement that, we are using a simple NOT gate to the slave. So this input of clock will be forwarded to the slave. Only when the slave will be getting a clock 0, at that time the slave will start working. So this is a simple block diagram. Now let's head with understanding a simple truth table of JK flip-flop. We can see here 0 0. The output will be same as that of a previous stage, and the operation, there is no change. Clear? Next, whenever we have a J is 0 and K is 1, at that time the output will be reset. Then whenever we are having 1 0, then our output will be 1, and that condition is called as set, then followed by 1 1. Whenever both the inputs are 1, then we had a toggling case, correct? So even here we will be having a toggle case, but in a minimized way, because of which there will be a controlled toggling. There will be no uncontrolled toggling and wasting of time and energy too. Here there will be a controlled toggling by using MSJK, that is by using master slave combinations. So this is all about MSJK flip-flop. Next, let's move forward and see next type of flip-flop, that is a T flip-flop. So T flip-flop is nothing but a toggle flip-flop, and we can see here it is a single input flip-flop developed by JK flip-flop by connecting J and K together as T, and it is called as toggle flip-flop. Yes, we know that whenever T is 1, the output will goes on toggling. It will work with a change in every clock pulse. Correct, right? Even in JK, it was the same thing. The inputs were dependent on the clock pulse. That is, the master and the slave was dependent even on the clock pulse too. So yes, let's see a simple block diagram. We have a single input, that is a T, followed by a clock. So clock is mandatory when you consider a sequential logic circuit. Okay, so the outputs, that is Q and Q dash. So this is a basic block diagram followed by logic diagram. Yes, let's see a logic diagram here. We are using 2 of the AND gates and 2 of the NOR gates in order to implement a T flip-flop, and you can see here the outputs, that is J and K, are considered and they are together provided as a input, that is a single input T, and we will be having 2 outputs, that is a Q as well as a Q bar. Now let's see a truth table. Yes, we can see the clock signals are high, and when the system or the flip-flop works, only when we will be having, that is 1 and 1, at that condition the output will goes from 0 1 1 to 0 according to clock. Okay, as we have only one clock, the present output is 0, but if we have a lower clock, at that time our output will go high. Okay, this is a simple truth table of a T flip-flop. We are almost done with the types of flip-flops, starting with SR flip-flop, JK flip-flop. Then we discussed MSJK flip-flop, then followed by our T flip-flop. Up next, let's see the decoders. So under decoder, we are studying 3 to 8 lines decoder. Yes, decoder is nothing but a combinational logic circuit. Even here, we will be having multiple inputs, and the main thing is the outputs. The output is dependent on input, but how is it? That is by using 2 power n unique outputs. So whenever if we consider we will be having n inputs, then our outputs will be 2 power n outputs. Decoder is a type of combinational logic circuit where it is used in order to define or consider inputs as well as outputs. But even here there is no feedback, there is no memory, nothing. Directly we will be giving the input and we will getting a output. Clear? The input and output, how is it correlated? So in order to understand that, let's see the block diagram. Here we have 3 to 8 decoders and the inputs are 3. Okay, 3 inputs, correct, right? What are those? S0, S1, S2. And we are having a enable signal. So this is a control signal. Okay. Up next, we will be having outputs, that is from D0 to D7, and this is none other than our 8 output bits. Now, let's see how this 3 to 8 condition, how is it possible? For that, we have a technique. So, if we have an input, okay, and at that time, we will be getting 2 power n outputs. So, for now, with respect to this decoder, the number of input lines are 3, right? The number of input lines are 3. So, for that, the output lines will be 2 power 3, which is none other than 8. So, for that, we will be getting the output from D0 to D7. This is a simple decoder, and we can say the decoder is having 3 inputs, that is S0 to S2, then followed by the outputs, 8 outputs, that is D0 to D7, and we have a simple enable bit which is a control signal. Okay, so this is all about a encoder. Now let's see how to write this in a truth table form. It is like we are having ABC, correct, which is considered as our input signals. It is a 3 input, correct? Now, what about the output? We have to get 8 output bits. But how is it possible? As we know 8, the combinations, or we can say, as we know, we are dealing with 3 of the inputs, the combinations will be 8 different combinations, right? Those 8 different combinations, that is starting with 40, 41, 20, 21, again 00, 11, followed by for C, it is 01, 01, 01. Great, it's done. Now, let's see how the output is written. So, here only those with active outputs will be considered. As all are 0, I can rewrite it as a D0, right? Up next, 001, it is none other than 1 bit, correct? So, we are writing it as D1. Next, it's 010, we are writing it as 2. Why is it 2? As we can know that it is like in 2 power 0, 2 power 1 and 2 power 2 format, which is none other than 1, 2, then followed by 4. Clear? Okay. So, this is with respect to 2. Then 011, it is none other than 2 plus 1, which is 3. Great. Then 100, so we have 1 at 4th bit, correct? It is D4. Then 101, which is none other than 4 plus 1, which gives us a value of 5. So, it is a D5. Followed by 110, which is a D6. Great, right? Followed by 111. When all the bits are high, we have to count all these 3. That is 4 plus 2, 6, 6 plus 1 is 7. So, it is a D7th bit. Great. If you want to represent this truth table in a form of expressions, so yes, even we can do that. As we know, we are having D0. So, for that D0, what are the input combinations? That is 0, 0, 0. So, we can write it as A dash, B dash, C dash. Is it right? Yes, D0 is none other than A dash, B dash, C dash. So, next D1, what is the input bits? 0, 0, 1. So, for this, the input is A dash, B dash and C. Alright. So, in the same way, we can go ahead and write the combinations for each and every output bit. So, this is all about a 3 to 8 decoder. When we understand about decoder, now it's time to move forward with the encoder. So, yes, under encoder, we will be learning octal to binary encoder, and even encoder is a type of combinational logic circuit itself. Here also there will be no feedback, no memory, nothing. There will be direct input and you'll be getting direct output. Here we have one twist, like the encoder is complete, a complemented form of a decoder. Like we had 8 output bits and 3 input bits in our decoder. Here it is completely opposite. We'll be having 8 input bits and only 3 output bits. So let's see it with an example. Over here you can see a block diagram, that is 8:3 encoder, where we will be having the 8 input bits followed by the 3 output bits, that is starting from A0, A1 as well as A2. Clear, right? So yes, this is all about a encoder. Now let's move forward and understand. Like what is a truth table and how to write the expression. It is almost the same thing. So as we are dealing with 8 number of inputs, we have to rewrite it in a form of 0001, okay, as it is a first bit. Next, for second bit, you'll put 1 under 2. For third bit, you'll put 1 for third one. Next, for fourth, you'll put 1 under that. For fifth, you'll only put 1 under fifth bit. Next, with respect to sixth row, you'll put 1 under Y6. For seventh row, you'll put 1 under seventh. Okay, that's under Y7. So this is how you'll be creating input bits. Now let's see how to write the outputs. As we know, with respect to the output, when we get a 1, that is Y0. So for 0, you have to write the value, that is 0, 0, 0. Next, for 1, what is the value? That is none other than 0, 0, 1. Again, you have to follow the same thing, 1, 2, 4. Okay. With this rule, you can go forward and write along with the number of. Let's go forward with the A1 expression. So in order to write the A1 expression, what we have to write is, we have to consider the bits, those which are worth 1. So for A1, we are having a 1 for Y2. Great, right? Next, for A1, we have 1 for Y3. Next, for A1, again we have got 1 under Y6. Great. Lastly, we have 1 under A1, that is for 7th bit. Alright, now let's see the expression. Is it the same? Are we getting? So for A1, we are having Y7 and Y6, then followed by Y3. Yes, Y2. So this is how we have to write the expression for A0, A1 and A2. This is all about a simple encoder. So whenever encoder or decoder is asked, you have to start writing like first define what it is, then followed by write a good block diagram, explain what is the number of outputs, what is the number of inputs, then what is the relation between input and output. So what is the relation between input and output? If you are dealing with decoder, then if you are having n number of inputs, the output will be 2 power n. That's with respect to encoder. Let's move forward with the encoder. What is it? If you are having 2 power n inputs, then the outputs will be n. Correct? So just explain the relation between input and output, then go forward with writing a truth table, then followed by the expression for each and every output. So this is all about an encoder and a decoder. And this encoder is also called as octal to binary. Why is it octal to binary? Because as you know, in octal, we will be dealing with only 3 input bits, and under binary, we are defining complete 8 bits, right? So that's why it is called as octal to binary encoder. Alright, so this is all about today's session, and in the upcoming session, we will be learning with respect to multiplexers, like what is a mux, and under that you will be having 4:1 mux, then followed by counters, and there is something also called shift registers. Thus, you'll be learning these things in our upcoming session. So this was with respect to this session. All right, thank you.